Hello and welcome to Physics Before Bed, your go-to place for diving into the fascinating world of science as we unwind and explore the mysteries of the universe. If you enjoy thought-provoking content like this, be sure to like and subscribe so you never miss an exploration of the incredible forces that shape the cosmos. And while you're here, let us know in the comments, where are you watching or listening from tonight? Are you perhaps listening from the comfort of your living room? Or maybe even from a distant corner of the globe where light from stars far away is just beginning to reach your eyes. It's interesting to think, no matter where you are in the world, the speed of a light connects us all, travelling through the vast emptiness of space, reaching across time itself. Tonight, we're going to ask a question that has puzzled scientists for centuries. Why does light travel at the exact speed it does? It's a question that stretches from the simplest of experiments to some of the deepest theories in modern physics. So sit back, relax, and let's take a journey into the incredible world of light, where the speed of this fundamental force just might be more than a constant. It could be the key to understanding the very nature of space-time and reality itself. Welcome to this fascinating exploration of a light's speed, a constant that has played a crucial role in shaping our understanding of the universe. For centuries, light has been a subject of fascination, and its speed, approximately 300,000 kilometers per second in a vacuum, has become one of the most fundamental constants in all of physics. But here's the thing, while it might seem like a simple, unchanging figure, we still don't fully understand why light travels at exactly that speed. And that's the question we'll be pondering together. Why does light travel at its specific speed, and why is that speed so crucial for everything from the cosmos to the tiniest particles in the quantum realm? It might seem like a question that could have a simple answer, but as we'll see, the answer opens up doors to some of the most profound and mind-bending concepts in physics. The speed of light isn't just a number, it is the speed limit of the universe. It's the speed at which all electromagnetic radiation, everything from radio waves to gamma rays, propagates through space. This single value connects ideas from the vastness of cosmology to the very small scale of quantum mechanics. In cosmology, it helps us measure the vast distances between galaxies, determining how far we can see into the past, as the light from distant stars takes millions, sometimes billions of years to reach us. In quantum mechanics, the speed of light is woven into the very fabric of the universe, setting the limits on how fast information or particles can travel. And in general relativity, light's speed is so deeply connected to the curvature of space-time that it helps determine how we understand gravity itself. To truly grasp why the speed of light is so central, we have to ask, why is that number so fixed? Why exactly 300,000 kilometers per second? To the untrained eye, light might seem like a simple phenomenon, but its speed isn't just a measurement, it's a piece of the puzzle that underpins the rules governing our universe. So how did we come to this number, and why does it remain constant? This question has been at the heart of some of the most revolutionary ideas in science. Of course, one of the first names that likely comes to mind when thinking about the speed of light is Albert Einstein. His famous theory of special relativity, developed in the early 20th century, revolutionized our understanding of space, time, and light. Einstein showed that the speed of light is constant for all observers, regardless of how fast they are moving. This idea led to the concept of space-time, where space and time are no longer separate entities but are intimately connected, and the speed of light sits at the heart of it all. It's what keeps our universe running smoothly and ensures that nothing can travel faster than light, no matter how massive, how energetic, or how far we might go. But while Einstein's work is undeniably central to our understanding, there's a rich history of scientists who laid the groundwork for these discoveries, and some fascinating perspectives that expand upon his theories. For instance, James Clerk Maxwell, a physicist from the 19th century, developed a set of equations that describe how electric and magnetic fields propagate through space. These equations led to the prediction of the speed of light as a constant. Essentially, Maxwell showed that light is an electromagnetic wave, and its speed is linked to the properties of the medium through which it travels. This was a major breakthrough, but it also posed a problem. If light is a wave, what medium is it travelling through? The answer was thought to be the ether, an invisible substance that filled all of space. However, when experiments like the famous Michelson-Morley experiment failed to detect any sign of the ether, scientists began to realize that light doesn't need a medium at all. It's its own thing, travelling through the vacuum of space at its fixed speed without relying on anything else. In the decades that followed, other scientists began to explore the implications of Maxwell's equations and Einstein's theory of relativity. For example, in the early 20th century, physicist Louis de Broglie proposed that all matter, not just light, has wave-like properties. This was a radical idea at the time and led to the development of quantum mechanics. In quantum mechanics, the speed of light plays an even more pivotal role, limiting the speed at which information can travel and ensuring that particles cannot exceed light speed. This limitation is crucial in preventing paradoxes, such as objects travelling backward in time or violating the causality of events. Yet, even with all the advancements in our understanding, questions about light speed remain. Is it possible that light speed isn't as constant as we think? Could it have been different in the early universe before the laws of physics as we know them took hold? These questions are at the frontier of modern physics, and ideas like the varying speed of light theory, proposed by João Magejo, suggest that light speed might not have always been the same. Some scientists have even speculated that light speed could be influenced by the fabric of space itself, meaning that the expansion of the universe or the curvature of space-time might alter how we experience the speed of light. There are also theories that challenge the very nature of space and time itself. Some physicists, drawing inspiration from quantum gravity, suggest that the speed of light might not be a fixed number at all, but instead, it could be subject to subtle changes depending on the scale of the universe we are looking at. Could light be a product of some deeper, yet unknown mechanism? Could it be that light speed is a byproduct of something more fundamental, something we have yet to uncover? These theories, while speculative, push the boundaries of what we know and suggest that light speed might still have some surprises left in store for us. In this journey of discovery, we'll explore these ideas in greater depth, looking not only at Einstein and Maxwell but at other fascinating scientists and their contributions, some well known and others less so, whose work has broadened our understanding of light. From Fizeau's early experiments with light in moving water to the radical ideas of physicists like de Broglie and Magejo, we will delve into the scientific exploration that has brought us to this point, and the exciting possibilities that lie ahead. So, settle in, relax, and let's embark on a journey to understand the speed of light, not just as a number, but as a key to unlocking the most profound mysteries of the universe. When we think about the history of light speed, the first names that often come to mind are Galileo Galilei and Albert Michelson. These pioneers, along with the remarkable work of others like Fizeau, Morley and Essen, shaped our understanding of light and its behaviour. However, the journey to fully comprehend light speed was a slow and steady accumulation of insights and experiments, each adding a small piece to a larger puzzle. So let's take a step back and explore some of these early contributions, and see how the seemingly simple question of how fast light travels became one of the central challenges in science. In the early days, the concept of light speed wasn't fully understood. Galileo, ever the visionary, was one of the first to try to measure the speed of light. He set up a rather clever experiment in the 16th century. Galileo and a companion would each hold a lantern, with one person covered and the other standing a certain distance away. When the person with the uncovered lantern saw the light, they would uncover their lantern in turn. The idea was to measure the time it took for the light to travel between them. But despite his ingenuity, Galileo couldn't measure the speed of light this way. The delay was simply too fast for their rudimentary methods to detect. This was the first indication that light moved far faster than they could measure at the time, but the actual speed of light remained a mystery. As the centuries passed, the race to determine the speed of light heated up. The next major breakthrough came in the early 19th century, thanks to the French physicist Hippolyte Fizeau. In 1849, Fizeau conducted a key experiment to measure the speed of light in a terrestrial setting. He used a rotating cogwheel and a beam of light reflected off a distant mirror. The idea was simple. By adjusting the speed of the rotating wheel and measuring the distance at which the reflected light would just miss the gaps in the wheel, Fizeau was able to calculate the speed of light. His result, about 313,000 kilometers per second, was remarkably close to the true value we know today, and it was a monumental leap forward in the understanding of light speed. Fizeau's experiment was a key moment, but it wasn't just the methods he used that were important. It was also the fact that he confirmed something fundamental about light. Its speed could be measured with increasing accuracy. At the same time, Fizeau was laying the groundwork for an even more profound discovery, one that would change the very nature of space and time itself. Around the same time, in the United States, a couple of scientists were quietly working away at their own experiments. One of them was Edward Morley, who worked with Albert Michelson on a series of crucial experiments in the late 19th century. Their goal was to measure the speed of light relative to the supposed ether, a hypothetical medium through which light was once thought to travel, much like sound travels through air. Michelson and Morley's work became iconic in physics, as their famous experiment in 1887 failed to detect any evidence of the ether. Despite the prevailing belief in the ether, their results suggested that light's speed was independent of any medium and would be the same regardless of motion. This was a pivotal moment in the history of science, signalling that the ether was unnecessary and that light's speed was truly a universal constant. Their null result laid the foundation for Einstein's theory of relativity, which would eventually explain why light behaves in this way. But it wasn't just Michelson and Morley's work that was groundbreaking. There were others who contributed to this crucial moment in physics. For example, in the mid-19th century, the German scientist Heinrich Hertz confirmed that light was indeed an electromagnetic wave, a concept first proposed by James Clerk Maxwell. Hertz's experiments demonstrated that light could be generated by oscillating electrical currents, which directly supported Maxwell's theory. This discovery brought a much-needed clarity to our understanding of light's nature. It wasn't just a strange, ethereal phenomenon. It was a form of electromagnetic radiation, governed by the same principles that govern electricity and magnetism. Fast forward to the early 20th century, and scientists like Albert Michelson, once again, would play a pivotal role in refining the measurement of light's speed. For his work, Michelson received the Nobel Prize in Physics in 1923, but his contribution was not just about measuring light's speed with ever-increasing precision. It was about challenging the very understanding of light's role in the universe. With his precise instruments, Michelson measured the speed of light in a variety of settings, and each measurement reinforced the idea that light was a constant, a key feature of the universe that didn't depend on the observer's motion or the medium through which it travelled. All these experiments were crucial for the scientific community, and they led to the final realization that the speed of light is the same everywhere, at all times, for everyone. But the most exciting part of this journey wasn't just discovering that the speed of light could be measured. It was what this constant meant for the universe itself. It would eventually lead to the profound understanding that the speed of light is tied to the fabric of space and time, and that the very structure of reality is shaped by this constant. The findings of these early experiments also set the stage for Maxwell's equations, which would eventually unify our understanding of light, electricity, and magnetism. Maxwell's equations describe the behavior of electromagnetic fields and how they propagate through space. His work showed that light was a form of electromagnetic radiation, and that its speed could be derived from these fundamental equations. The speed of light, it turns out, is not an arbitrary number. It's a direct consequence of the properties of the electromagnetic field itself. The link between experiment and theory was finally realized. What had once been a question of measurement became a question of understanding the underlying mechanisms. Maxwell's equations, developed in the mid-19th century, provided the framework that linked the speed of light to the basic laws of electromagnetism. Through this, light's speed was revealed not as a simple value to be measured, but as a manifestation of the deep, unchanging properties of the universe. These early breakthroughs were not just about measuring a number, they were about understanding how light fits into the larger puzzle of the universe. The failure to detect the ether, the determination that light's speed was constant, and the later connection of light to the electromagnetic field laid the foundation for Einstein's theory of relativity. In relativity, light's speed becomes a cornerstone of space and time, shaping the very fabric of reality. So, as we look back at the contributions of Fizeau, Morley, Michelson, and others, it's important to see them not just as isolated experiments, but as part of a larger interconnected story. Each experiment built upon the last, and together they led us to a profound realization. Light speed is not just a number, it is a key to understanding the deepest mysteries of the universe, linking the world of the very small to the vast expanses of space. Through their hard work and ingenuity, these scientists not only measured the speed of light, but helped us understand why it's so fundamental to the universe itself. In the 19th century, the idea of light being a wave was gaining momentum. Prior to this, the prevailing view was that light might be composed of particles, as suggested by scientists like Isaac Newton. But as experiments began to refine our understanding, a different idea began to take shape. Light is not just a beam of particles, but a wave, and not just any wave, but an electromagnetic one. The key to unlocking this understanding came from the work of James Clerk Maxwell, a Scottish physicist who, in the mid-19th century, unified the principles of electricity, magnetism, and light into a single framework. Maxwell's equations, as they came to be known, were groundbreaking. These 4 equations described how electric and magnetic fields interact, how they are generated and altered by each other, and how they propagate through space. What was truly remarkable, however, was what Maxwell's equations predicted about the nature of light. One of the key predictions Maxwell made was that light is an electromagnetic wave. This was more than a theory. It was a prediction grounded in mathematical elegance. According to Maxwell, changing electric fields could generate magnetic fields and vice versa. Together, these oscillating fields could propagate through space as a wave. The wave's speed, according to Maxwell's equations, was directly related to 2 fundamental constants of nature: the electric constant, which describes how electric fields interact with matter, and the magnetic constant, which describes the interaction of magnetic fields. But it didn't stop there. Maxwell's equations not only predicted that light was an electromagnetic wave, but they also predicted that these waves would travel through a vacuum at a specific speed. This was the crucial part. The speed of light, in Maxwell's framework, wasn't just a random number, it was tied to the properties of space itself. The exact speed of light was determined by the relationship between these electric and magnetic constants. Maxwell's equations showed that the speed of light in a vacuum would be approximately 300,000 kilometers per second. Now, you might wonder why this was such a revolutionary moment. Up until this point, scientists had measured the speed of light, but they didn't fully understand why it was what it was. Maxwell, however, showed that the speed of light was not just a number we happen to measure, but something fundamental about the universe itself. The speed of light was determined by the properties of space, by how electric and magnetic fields interacted with each other. What's even more remarkable is that Maxwell's equations didn't just describe light, they predicted it. The idea that light is an electromagnetic wave was not a postulate, but a natural outcome of his mathematical work. It tied together the fields of electricity and magnetism, which were previously thought to be separate, and revealed that light is just one of many possible types of electromagnetic radiation. Light is a small part of a vast spectrum that includes radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. All of these are electromagnetic waves, but they differ in their frequency and wavelength. The only thing that set visible light apart was the specific frequency range that our eyes can detect. As groundbreaking as Maxwell's equations were, they didn't just explain light, they hinted at something deeper. One of the most fascinating aspects of his theory is that it suggested light could travel through a vacuum free from any material medium. This was in stark contrast to earlier theories, such as the ether theory, which posited that light needed a medium to travel through. The ether was thought to be a substance that filled all of space, allowing light to propagate like sound travels through air. But Maxwell's equations didn't require such a medium. Light could travel through the emptiness of space itself. This idea would later become crucial for Einstein's theory of special relativity, but at the time, it was a surprising and bold insight. While Maxwell was working on his equations, other scientists were refining the experimental understanding of light's behavior. 2 figures stand out in particular: Oliver Heaviside and Hermann von Helmholtz. Heaviside, an English electrical engineer, helped simplify Maxwell's equations, making them more accessible and easier to work with. Heaviside's work showed that the equations weren't just theoretical curiosities. They could be used to predict real-world phenomena, such as the behavior of electrical circuits and electromagnetic waves. Helmholtz, a German physician and physicist, was another important figure. He made key contributions to understanding the conservation of energy in electromagnetic systems, and his work laid the groundwork for future developments in thermodynamics and electrical engineering. Together, these scientists helped turn Maxwell's abstract equations into a practical tool for understanding the behavior of light and other electromagnetic waves. At this point, light was firmly understood as an electromagnetic wave, but there was still much more to uncover. One of the most intriguing ideas that came out of Maxwell's work was the concept of light as a higher dimensional phenomenon. This wasn't a mainstream view at the time, but it was one that would come to be explored more fully later in the 20th century. The basic idea is that light's behavior could be understood not just in three-dimensional space, but in higher dimensions, a concept that has gained traction in the context of string theory. String theory, a leading candidate for a theory of everything, proposes that the fundamental building blocks of the universe aren't particles, but tiny vibrating strings of energy. These strings exist in a higher dimensional space, with dimensions beyond the familiar 3 of space and 1 of time. In this framework, the speed of light could be viewed as a consequence of the way these strings vibrate and interact with each other. This speculative view of light ties into the work of Theodor Kaluza, a German mathematician who, in the 1920s, proposed a 5-dimensional space-time model that combined electromagnetism with gravity. Kaluza's work was a precursor to the ideas that would eventually lead to string theory and the search for a unified theory of the fundamental forces. But let's not get too carried away just yet. At the time of Maxwell, this higher dimensional view of light was far from being a mainstream idea. What Maxwell's equations did, however, was provide a framework that would inspire future generations of scientists to think about light in new and profound ways. It showed that light wasn't just a simple phenomenon, it was deeply tied to the fundamental structure of space itself. As we move forward in the history of physics, the next big leap would come with the work of Albert Einstein and his theory of relativity. Einstein would take Maxwell's insights about the constancy of the speed of light and use them to revolutionize our understanding of space, time, and gravity. But before Einstein could do that, Maxwell had already set the stage by showing that light is more than just a wave. It's an intrinsic feature of the universe, tied to the very fabric of space-time. In Maxwell's world, light wasn't just an oddity or a curiosity, it was a clue to understanding how the universe operates. The speed of light was not just a measurement, it was a fundamental constant that told us something deep about the nature of the universe. It's hard to overstate just how profound this realization was. For centuries, light had been a mysterious and elusive phenomenon. But thanks to Maxwell, Heaviside, Helmholtz, and many others, light was no longer just a source of wonder. It was now something that could be studied, understood, and even predicted. So as we look back at Maxwell's work, it's clear that his equations didn't just give us the speed of a light, they gave us the key to unlocking the entire world of electromagnetic radiation, from the waves that power our radios to the light that illuminates our skies. And in doing so, they set the stage for the next great leap in physics, the discovery that light speed is not just a number, but a cornerstone of the very structure of reality itself. In the early 20th century, one of the most profound shifts in our understanding of the universe occurred, thanks to a man named Albert Einstein. Up until this point, scientists had been working within a framework that assumed space and time were separate, unchanging entities. But Einstein's special theory of relativity, introduced in 1905, shattered that view and showed the world something truly extraordinary, that the speed of light is constant, no matter who is measuring it or how fast they are moving. Before Einstein, most people believed that if you were moving toward a light source, the light would appear to move faster relative to you. Similarly, if you were moving away from the light, it would appear to move slower. But Einstein turned this notion on its head by proposing that no matter how fast you're moving, whether toward or away from the light, the speed of light remains the same. It's always 300,000 kilometers per second in a vacuum, no matter the observer's motion. This idea was revolutionary. It was a direct challenge to the intuitive notions of space and time that had dominated physics for centuries. The implications of this were profound. For one, it meant that space and time were not fixed and independent. Instead, they were deeply intertwined, forming what we now call space-time. This was the key insight of Einstein's special relativity. Space and time are not separate entities, but rather a single four-dimensional continuum. Space and time, instead of being rigid, could bend and stretch in response to motion and gravity. This meant that the fabric of the universe itself could be altered by the motion of objects, something that would have been unimaginable in the classical view of physics. Einstein's theory was not created in isolation. There were many others, both before and during his time, who contributed ideas that helped make this shift in perspective possible. One such figure was Hermann Minkowski, a German mathematician who in 1908 introduced the concept of space-time in a more formalized way. Minkowski's work showed that Einstein's special relativity could be understood in terms of a four-dimensional space, where time was treated as another dimension, just like the three spatial dimensions. Minkowski's geometric interpretation was crucial for understanding the full implications of Einstein's ideas, and it made the concept of space-time much more tangible. Without Minkowski's insight, it's likely that Einstein's theory would have remained a collection of abstract ideas without the solid geometric foundation that would allow it to reshape physics forever. But let's take a moment to think about why the constancy of light's speed is so radical. Light's speed, unlike the speed of any other object in the universe, is not dependent on the motion of the observer. If you're driving down the highway and you see a car moving toward you at 100 km per hour, the speed of that car depends on your own speed. If you're moving in the same direction as the car, it will appear to move slower. But light doesn't behave this way. Whether you're moving toward a light source or away from it, the light always travels at the same speed. This means that time and space themselves must adjust to accommodate this constant speed, and that's where the theory of relativity comes in. This brings us to the idea of time dilation. According to special relativity, as an object moves closer to the speed of light, time for that object slows down relative to an observer at rest. This is known as time dilation. For example, imagine a spaceship traveling close to the speed of light. If you were to look at a clock aboard the spaceship, you would see it ticking more slowly than a clock on Earth. From the perspective of someone aboard the spaceship, however, time would seem normal to them. This phenomenon has been confirmed in many experiments, such as those involving atomic clocks flown around on airplanes. When they are compared to identical clocks on the ground, the clocks on the airplanes show that time has passed more slowly for them. This is not science fiction. This is the real effect of special relativity. Another consequence of special relativity is length contraction. This is the idea that, as an object approaches the speed of light, its length in the direction of motion appears to contract or shrink from the perspective of a stationary observer. If you were in a spaceship moving at nearly the speed of light, you would not notice the contraction of your own spaceship. However, an observer on Earth would see it appear shorter. This, like time dilation, is a direct result of the constancy of light's speed. Space and time are not immutable. They stretch and contract in response to motion. Together, time dilation and length contraction show how space and time are intertwined, bending and adjusting to the motion of objects within the universe. Now, while the constancy of light speed seems strange, and the implications it has on space and time are mind-boggling, it's important to remember that this theory has been confirmed time and time again. One of the most famous experiments to confirm Einstein's predictions came in 1914, when the British astronomer Arthur Eddington observed the bending of light around the Sun during a solar eclipse. According to Einstein's general theory of relativity, gravity could bend light's path, and Eddington's observations confirmed this. The bending of light by gravity wasn't just a theoretical prediction, it was something that could be measured and observed in real life. At this point, we're starting to see how the understanding of a light's speed is not just a curious detail, but something that shapes the very fabric of reality. Light speed, as it turns out, is a cornerstone of physics, and its constancy influences everything from time itself to the way we perceive space. But while special relativity gives us a new understanding of space and time, there's still more to explore, especially when it comes to gravity. This is where general relativity comes in. While special relativity dealt with objects moving at constant speeds in a straight line, general relativity extends these ideas to include acceleration and gravity. It tells us that gravity is not just a force between masses, as Newton suggested, but a warping of space-time itself. Objects like planets and stars cause the fabric of space-time to curve, and this curvature affects the path that light takes. In fact, light's speed is still crucial in general relativity, because the bending of light around massive objects is dependent on the relationship between light's speed and the curvature of space-time. Einstein's theory of general relativity would provide a deeper understanding of light's behavior, particularly when it comes to the way light interacts with massive objects such as black holes. In general relativity, the speed of light becomes even more significant, as it sets the limit for how quickly information can travel across the universe. As we will explore in the next chapter, general relativity helps us understand the relationship between light and gravity in profound ways, opening the door to new discoveries about the very nature of the universe. Einstein's special theory of relativity didn't just change our understanding of light, it changed our entire conception of space, time, and the universe. Light speed, once just a number, became a cornerstone of our understanding of the cosmos, helping to shape the modern theories of physics that continue to guide scientific inquiry today. Through the work of Einstein and others, we now know that light speed is more than just a constant. It is a key to unlocking the deepest mysteries of reality. And as we move forward, that understanding will continue to evolve, revealing new truths about the universe that are just waiting to be discovered. When Albert Einstein introduced his general theory of relativity in 1915, he not only transformed our understanding of gravity, but also brought new insights into the relationship between light and gravity. According to general relativity, gravity isn't a simple force acting at a distance as Newton had proposed. Instead, it is the result of massive objects curving the very fabric of space and time, a concept that Einstein called space-time. This curvature affects not only objects with mass, but also the path of light itself. Now, you might think that light, being massless, would be unaffected by gravity. After all, light doesn't have mass, so how could it be influenced by the same forces that shape planets and stars? But this is where Einstein's theory really shines. Even though light has no mass, it still follows the curvature of space-time, and that means its path can be bent by the presence of massive objects. In other words, gravity can affect light, even though light doesn't have mass. One of the first applications of Einstein's theory came in the form of a prediction about how light would behave near a massive object like the Sun. In fact, one of the earliest tests of general relativity came in 1914, when British astronomer Arthur Eddington observed a solar eclipse. During the eclipse, Eddington and his team were able to measure the deflection of starlight as it passed near the Sun. According to Einstein's equations, light passing close to a massive object like the Sun should be bent, just as a ball would follow a curved path if it were rolling on a curved surface. The results of Eddington's observation confirmed Einstein's prediction. Light, even though massless, was indeed bent by gravity. This bending of light is a key concept in general relativity, and it's known as gravitational lensing. When light passes by a massive object like a galaxy or a black hole, the object's gravitational field distorts the light's path, much like how a lens can bend light. This effect can create a magnifying or distorting effect, making distant stars or galaxies appear larger, distorted, or multiple. Gravitational lensing provides scientists with a powerful tool to study objects that are otherwise too far away or too faint to see directly. By observing the way light is bent by the gravitational influence of distant objects, astronomers can learn about the mass, shape, and distribution of those objects. The most dramatic example of gravitational lensing occurs around black holes. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape. When light passes near a black hole, its path is bent so severely that it can be trapped, looping around the black hole in a process known as gravitational capture. In some cases, light can be bent around a black hole multiple times, creating a phenomenon known as an Einstein ring. A perfect ring of light around the black hole, a visual echo of light that has travelled through curved space-time. The idea that light can be bent by gravity is a fundamental aspect of general relativity, but it also opens up some intriguing possibilities for the behaviour of light in extreme environments. As light approaches a black hole, its path becomes more and more distorted. In fact, as light moves closer to the event horizon, the point beyond which nothing can escape, a phenomenon known as gravitational redshift occurs. Light that is emitted from a source near a black hole is stretched out, or redshifted, to longer wavelengths as it climbs out of the gravitational well. If you were to observe this light from far away, you'd see it become dimmer and shift toward the red end of the spectrum, as if the light were losing energy. This is another of Einstein's predictions that has been confirmed by observations of black holes and other dense objects. Now, while general relativity has revolutionized our understanding of light and gravity, there are still some unanswered questions. The theory works remarkably well in most situations, but it doesn't fully explain what happens in certain extreme conditions, such as inside black holes or in the very early universe. For example, we know that light behaves in a certain way near a black hole, but what happens to light when it crosses the event horizon and is trapped forever? This is where some alternative theories begin to come into play. One such alternative theory comes from Eric Verlinde, a Dutch theoretical physicist, who has proposed what is called emergent gravity. Verlinde's theory suggests that gravity might not be a fundamental force at all, but rather an emergent property of other phenomena. According to this view, gravity arises from the entropic forces associated with the distribution of information in the universe. In this framework, light's behavior could be influenced by the way gravity emerges from these deeper underlying forces. While this theory is still speculative and not widely accepted, it challenges some of the assumptions of general relativity and could offer new insights into how light interacts with gravity in extreme environments. Verlinde's theory, along with other ideas in the realm of quantum gravity, suggests that there may be deeper layers of reality yet to be discovered. As we continue to explore the universe and push the boundaries of science, questions about the nature of gravity, light, and space-time will likely continue to evolve. We may find that our current understanding, while incredibly successful, is just the beginning, and that the true nature of light in the presence of intense gravitational fields is far more complex than we can yet imagine. At the heart of these questions is the speed of light itself. Light speed is the constant that ties together our understanding of space, time, and gravity. It's the boundary that governs the way information and matter can travel through the universe, and it plays a crucial role in how we understand the forces that shape the cosmos. Whether it's the bending of light around a galaxy, or the stretching of light near a black hole, the behavior of light in the presence of gravity gives us a glimpse into the deep structure of the universe. As we move further into our exploration of light and its relationship with gravity, there are still many questions to answer. What happens to light near the event horizon of a black hole? How does light behave in the very early universe, when gravity and quantum mechanics might be intertwined in ways we don't yet fully understand? These are questions that scientists are working hard to answer, and they will be the focus of future research and discovery. For now, we can appreciate the beauty and complexity of light's dance with gravity. The bending of light around massive objects, the way light escapes from black holes, and the new theories that challenge our understanding of gravity all point to a deeper connection between light and the universe's most fundamental forces. As we continue to unravel these mysteries, light will remain our guide, illuminating the path toward new discoveries about the very nature of reality itself. As we turn our gaze from the intricacies of light's behavior in the presence of gravity to the vast expanses of space itself, the speed of light continues to play a pivotal role in shaping our understanding of the cosmos. In cosmology, light's speed is not just a number we use to measure distances. It is a crucial factor in how we perceive the universe's very structure. It affects how we observe distant galaxies, how we understand the expansion of the universe, and how we unravel the history of the cosmos itself. One of the most profound implications of the speed of light in cosmology is the concept of redshift. When light travels through space, it stretches out, particularly when it moves away from us. This stretching, or redshifting, happens because the universe is expanding. As light moves through expanding space, its wavelength grows longer, shifting toward the red end of the spectrum. This redshift is not just a neat optical illusion. It's a direct result of the fact that light's speed remains constant, no matter how far the light has traveled or how fast the source is moving. The phenomenon of redshift allows us to measure the rate at which the universe is expanding, and it was crucial to the development of modern cosmology. The discovery of redshift in the light from distant galaxies was a key observation that led to the realization that the universe is not static but is constantly expanding. In fact, in the 1920s, American astronomer Edwin Hubble, using redshift measurements, observed that galaxies are moving away from us, and the farther they are, the faster they appear to be receding. This observation became known as Hubble's law, and it fundamentally changed how we viewed the universe, pointing to an expanding cosmos where space itself was stretching out. The work of Alexander Friedmann and Georges Lemaître further deepened our understanding of the expanding universe. Friedmann, a Russian mathematician, and Lemaître, a Belgian physicist and priest, independently proposed models for an expanding universe in the early 20th century. Friedmann's equations showed that the universe could not be static, but must be either expanding or contracting. Lemaitre went further to suggest that the universe began from a singular point, a primeval atom, which would later evolve into the expansive universe we see today. Their ideas were groundbreaking, and they laid the foundation for what would eventually become the Big Bang theory. Their work showed how the speed of light, along with the expansion of space, allows us to trace the universe's history, seeing further back in time as we look at more distant galaxies. The light from these faraway galaxies is like a snapshot of the past, and because light takes time to reach us, the farther we look, the further back in time we're seeing. But while the observation of redshift helped solidify the theory of an expanding universe, it also raised more questions about the role light speed played in the early cosmos. Could the speed of light have been different in the early universe? What if light's speed changed over time, potentially influencing the development of the universe in ways we hadn't considered? This idea is at the heart of the varying speed of light, VSL theory, a speculative idea proposed by João Magejo and others in the late 20th century. The VSL theory suggests that the speed of light was not constant in the early universe, but may have been much faster, particularly during the period known as cosmic inflation. Cosmic inflation is a theory that proposes that the universe underwent an extremely rapid expansion in the first moments after the Big Bang, stretching by a factor of at least 1 trillion in just a fraction of a second. The idea behind VSL is that during this period of inflation, the speed of light might have been much greater than it is today, allowing for the rapid spread of energy and matter throughout the universe. If this were the case, it could explain some of the mysteries of the early universe, such as the uniformity of the cosmic microwave background radiation, the smoothness of the universe at large scales, and the problem of horizon distance. While the VSL theory is still highly speculative, it opens up intriguing possibilities for how light's speed might have influenced the formation of the universe. If light were indeed faster in the early universe, it could have played a role in shaping the distribution of matter and energy, potentially providing a mechanism for inflation to occur. It also raises the question of how much we truly understand about the nature of light itself. Could it be that light speed is not a constant after all? Or is there a deeper, more fundamental principle at play that we have yet to uncover? One thing that's clear is that the speed of light is intimately tied to the universe's observable properties. The expansion of space, the redshift of light, and the way we observe distant galaxies are all influenced by this fundamental constant. The idea that light's speed could have been different in the early universe is just one example of how our understanding of the cosmos continues to evolve. It's also a reminder of how much we still have to learn about the nature of light itself and how it fits into the larger framework of the universe. As we consider the possibility of varying light speeds, it's worth noting that the speed of light also influences the very formation of the universe. The speed at which light travels determines how far we can see into the past. When we observe distant galaxies, the light we see has travelled billions of years to reach us, giving us a glimpse into the early history of the universe. But if light's speed were different in the past, it could change the way we interpret those observations. For example, a faster speed of light in the early universe could mean that the universe's expansion happened much more quickly than we currently think, which would have profound implications for how we understand the timeline of cosmic events. The speed of light also plays a role in how we measure the size of the universe and understand its geometry. The fact that light travels at a constant speed gives us a reliable tool for measuring distances across the cosmos. Using light, we can calculate the distances to stars, galaxies, and even the farthest reaches of the observable universe. The speed of light, therefore, isn't just a number. It's the key to measuring the universe itself. As we continue to explore the nature of light in cosmology, we must also consider the possible ways in which light interacts with other forces, especially at extremely small scales. In the next part of our journey, we'll dive into the realm of quantum mechanics, where light's behavior takes on a whole new set of rules. But before we get there, it's clear that light's speed has shaped the universe in profound ways, from the very beginning of the cosmos to the vast expanding universe we observe today. The speed of light, as constant and fundamental as it may seem, continues to reveal mysteries that challenge our understanding of the universe. Whether it's the way light bends around massive objects, the possibility of varying light speeds in the early universe, or the fundamental role it plays in the fabric of space-time itself, light remains a powerful tool for exploring the deepest questions in physics. And as we push further into the unknown, light will continue to guide us, illuminating the path to new discoveries. Quantum mechanics, the branch of physics that deals with the behavior of the tiniest particles in the universe, challenges many of our conventional ideas about how things should behave. When it comes to light, this is especially true. At the macroscopic scale, we have a clear understanding of how light behaves. It travels at a constant speed of 300,000 kilometers per second in a vacuum, and this speed is central to our understanding of the universe. However, when we step into the microscopic world of quantum mechanics, light's behavior becomes much more complex and less predictable. One of the key features of quantum mechanics is that it introduces a sense of uncertainty and non-locality, ideas that defy our classical intuitions. For example, particles at the quantum level don't have definite positions or velocities until they are measured. Instead, they exist in a cloud of probabilities, and only when we observe them do they collapse into a definite state. This uncertainty is known as Heisenberg's uncertainty principle, and it introduces a new way of thinking about the universe, where the exact properties of particles can't be known simultaneously with absolute certainty. This principle doesn't just apply to particles, it applies to light as well. David Bohm, a physicist whose work often gets overlooked in mainstream discussions of quantum theory, offered a radically different perspective on quantum mechanics. Bohm introduced the concept of a quantum potential, a non-local field that guides particles even when they are separated by vast distances. His idea suggested that the universe might be much more interconnected than we previously thought, with hidden connections between distant events that we don't yet fully understand. In this framework, the speed of light might not be a simple constant, but could be affected by the quantum potential itself. In Bohm's view, the universe is more like a holographic system, where each part of the universe contains information about the whole, and light might travel through a deeper underlying reality that we have yet to fully grasp. Bohm's ideas introduced a concept of non-locality, which means that particles can influence one another instantaneously, no matter the distance between them. This idea is famously illustrated by the phenomenon of quantum entanglement, where two particles can become so deeply connected that the state of one particle directly affects the state of the other, even if they are light years apart. The concept of entanglement challenges our traditional ideas of space and time, where interactions are supposed to be limited by the speed of light. In quantum entanglement, information seems to travel faster than light, an idea that Einstein famously described as spooky action at a distance. While the phenomenon of entanglement doesn't allow for faster-than-light communication, it does suggest that there might be aspects of the universe where the rules we've come to accept don't apply in the same way. The behavior of light, as it relates to entanglement and non-locality, hints that light might be part of a deeper quantum fabric of the universe, where the speed of light could be influenced by more fundamental hidden forces. In addition to Bohm's ideas, quantum field theory, QFT, plays a crucial role in our understanding of light at the quantum level. QFT is the framework that combines quantum mechanics and special relativity to describe the interactions of particles as fields. In this theory, light is not just a wave traveling through space. It is a quantum field that permeates the entire universe. Photons, the particles that make up light, are excitations or disturbances in the electromagnetic field, and these disturbances move at the speed of light. According to QFT, the speed of light emerges as a result of the properties of the electromagnetic field, which is deeply connected to the structure of spacetime itself. The constant speed of light that we observe at macroscopic scales is the result of the dynamics of these quantum fields, which are governed by the fundamental constants of nature. However, when you move to extremely small scales, such as the Planck length, the idea of a constant speed for light may begin to break down. At these scales, where quantum effects dominate, the behavior of light could be influenced by quantum fluctuations in the fabric of spacetime itself. One of the most intriguing aspects of quantum field theory is that it suggests that the speed of light, while constant at the scale we observe, may not be a fixed quantity in all circumstances. Some quantum theories propose that the speed of light could vary depending on the energy scales involved, or the specific conditions of spacetime. For example, some researchers have speculated that, in the very early universe, light might have travelled at a speed much greater than it does today, possibly in the context of a high-energy environment created during the Big Bang. The idea of a varying speed of light is part of a broader group of theories known as varying speed of light, VSL theories. These theories suggest that the speed of light was different in the early universe, particularly during periods of rapid cosmic inflation. According to the VSL hypothesis, the speed of light could have been much faster in the moments after the Big Bang, allowing for the rapid expansion of the universe that is required to explain the uniformity of the cosmos at large scales. In these early moments, light's speed could have played a crucial role in shaping the structure of the universe, influencing the distribution of matter and energy. If light's speed was indeed faster in the past, this would have profound implications for our understanding of the universe's formation. It could change the way we think about the early universe and the processes that drove the Big Bang. The speed of light would have had a direct impact on the way information and energy spread throughout the cosmos during these formative moments. If the speed of light were faster, it might have allowed for the rapid equilibration of temperature and density across the universe, smoothing out any irregularities that might have existed in the early universe. This could help explain the uniformity of the cosmic microwave background radiation that we observe today. While VSL theories are still highly speculative, they push the boundaries of our understanding and challenge our conventional ideas about the nature of light. The possibility that the speed of light could change depending on the energy scale or the time in the universe's history opens up new avenues of exploration for physicists. It's a reminder that, while our current understanding of light speed is based on solid experimental evidence, there may still be much more to discover about this fundamental constant. At the quantum level, the speed of light is not just a number to be measured, it is a key player in the deeper workings of the universe. As we continue to investigate the behavior of light in extreme conditions, both in the early universe and in the depths of quantum mechanics, we are bound to encounter new ideas and revelations. The speed of light may not be the fixed, unchanging constant that it appears to be on the macroscopic scale. Instead, it may be part of a much more intricate and dynamic picture, shaped by the hidden forces and interactions that govern the quantum world. As we move forward, the exploration of light's speed at the quantum scale will be one of the most exciting frontiers in physics. Whether we are looking at the early moments of the universe, exploring the depths of quantum fields, or investigating the potential of new theories like VSL, the speed of light will continue to be a key concept that guides our quest for understanding the fundamental nature of reality. It is a constant, but it may also be far more complex than we've ever imagined, and it is only through continuing to challenge our assumptions that we will unlock the deeper secrets of the universe. For centuries, scientists have understood the speed of light as a constant, a fundamental pillar of physics. It has shaped much of our understanding of space, time, and the very structure of the universe. But what if this constant isn't as fixed as we think? What if, at certain times or under specific conditions, the speed of light could change? This is the idea that has spurred some intriguing research, particularly in the realm of cosmology, where the speed of light's behavior could hold answers to some of the universe's most profound mysteries. One of the key figures in this line of inquiry is João Magejo, a Portuguese theoretical physicist whose work on the varying speed of light, VSL, theory challenges the traditional view. Magejo proposed that, in the early universe, the speed of light may have been much faster than it is today. In fact, his theory suggests that light's speed could have varied during different epochs of the universe's development. The idea of varying light speeds, while speculative, is an exciting possibility that could explain some of the persistent puzzles in cosmology, particularly around the rapid expansion of the universe shortly after the Big Bang. Magejo's VSL theory was inspired by the need to explain some of the peculiarities of cosmic inflation. Cosmic inflation is the theory that in the first few moments after the Big Bang, the universe expanded exponentially, much faster than we can observe today. This sudden, immense growth would have caused the universe to become remarkably uniform, with the same temperature and density spread across vast distances. However, traditional models of physics couldn't easily explain how this rapid expansion occurred without violating causality or other physical laws. The idea of varying the speed of light offers a potential solution. If the speed of light were faster in the early universe, it could have allowed for faster communication between distant regions, facilitating the uniformity we observe today. The implications of this theory are far-reaching. If the speed of light was indeed faster in the past, it would rewrite many of our assumptions about the laws of physics. The constancy of light's speed is embedded in both general relativity and quantum mechanics, so any deviation from this would have profound consequences for our understanding of space-time, gravity, and the very fabric of reality. It would also challenge the principle of relativity itself, which states that the laws of physics are the same for all observers, regardless of their motion. A variable speed of light could fundamentally alter the way we think about everything from the structure of the cosmos to the nature of the forces governing the universe. In recent years, scientists have been looking for experimental evidence to support, or refute, McGeehow's theory. One of the most promising areas of research is the study of the cosmic microwave background, CMB, radiation. The CMB is the afterglow of the Big Bang, and it provides a snapshot of the universe when it was just a few 100,000 years old. By analysing the patterns and fluctuations in the CMB, scientists can learn about the early universe's temperature, density, and expansion. Some researchers believe that changes in the speed of light during inflation could leave subtle imprints in the CMB, which could be detected by modern telescopes. One of the challenges in detecting these potential variations is that the speed of light is incredibly difficult to measure directly on cosmic scales. Light travels at such a vast speed that even the smallest variations would be hard to detect with current technology. However, astronomers have used a number of clever techniques to study light from distant galaxies, looking for signs of any changes in its speed over time. For example, measurements of redshift in the light from distant quasars and galaxies could reveal whether light has been traveling at a slightly different speed as it journeys across the universe. The idea that light's speed could vary also opens the door to new possibilities in the realm of dark matter and dark energy, two of the most mysterious phenomena in cosmology. Dark matter, which makes up a large portion of the universe's mass, interacts with gravity but doesn't emit or absorb light. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe. These two forces are fundamental to our understanding of the cosmos, but they remain largely unexplained. If light's speed were influenced by dark matter or dark energy, it could provide a new way to link these elusive phenomena to the more familiar forces we can observe directly. One speculative idea that has emerged from this is that the presence of dark matter might alter the fabric of space-time in such a way that the speed of light could fluctuate. This could be particularly relevant in the very early universe, when dark matter played a more prominent role in shaping the structure of the cosmos. Similarly, dark energy, which is driving the universe's accelerated expansion, could potentially have an effect on the behavior of light across vast distances. While this remains speculative, the very fact that light's speed might be influenced by these unseen forces opens up new avenues for research in cosmology and beyond. Another interesting line of inquiry comes from the study of quantum field theory, or QFT, which combines quantum mechanics and special relativity to describe the interactions of particles and fields. QFT suggests that light isn't just a simple wave traveling through space, it is a quantum field that permeates the entire universe. In this framework, the speed of light is an emergent property of the quantum fields, determined by the dynamics of those fields. It's possible that, under extreme conditions such as near black holes or during the early moments of the Big Bang, these quantum fields could behave in ways that cause the speed of light to change. The idea that the speed of light could vary at quantum scales or during cosmic events is exciting, but it's also incredibly difficult to test. At the quantum level, light behaves in ways that challenge our classical understanding. It exhibits both wave-like and particle-like properties, and its interactions with matter are governed by the principles of quantum mechanics, which are still not fully understood. Understanding how light behaves in these extreme conditions requires developing new theories and technologies that can probe the fabric of space-time at much smaller scales than we can currently access. Despite the challenges, the search for variations in light speed could lead to groundbreaking discoveries that change our understanding of the universe. If we were to find evidence that light speed varies, it would have profound implications for the laws of physics, possibly requiring us to rethink our understanding of space, time, and the fundamental forces that govern the cosmos. It could also provide new insights into the mysteries of dark matter, dark energy, and the early universe, offering a deeper connection between the known and unknown aspects of reality. As we continue to investigate the nature of light and its speed, we are constantly pushing the boundaries of science. The search for variations in light speed is just one example of how we are challenging our current understanding and exploring the deeper truths of the universe. Whether through the study of cosmic radiation, experiments in particle physics, or the search for dark matter, the quest to understand light's behavior in all its forms will continue to shape our view of the cosmos in exciting and unexpected ways. As we look to the future, the mysteries of light, space, and time will undoubtedly reveal new wonders that challenge our imagination and deepen our understanding of the universe we call home. As we continue to explore the fascinating world of light, one of the most mind-bending concepts that emerges from Einstein's theory of relativity is how the speed of light influences the very nature of time and space. Time dilation and length contraction are two of the most important and surprising consequences of this idea. These effects show us that time and space are not fixed, unchanging realities. They are malleable and influenced by the speed at which we move. In fact, as objects approach the speed of light, the fabric of space-time itself begins to warp and bend in ways that defy our everyday experience. Time dilation is perhaps the most famous of these relativistic effects. Simply put, it means that time moves differently for objects that are moving at speeds close to the speed of light. The faster an object moves, the more slowly time appears to pass for it, relative to a stationary observer. This is a profound departure from our everyday experience, where time seems to flow at a constant rate for everyone, regardless of how fast they are moving. Imagine a spaceship traveling at a speed close to the speed of light. If you were aboard the spaceship, everything would feel perfectly normal to you. Your clock would tick at the same pace, and your heartbeat would follow the same rhythm. But if someone were watching you from Earth, they would notice something very strange. To them, your clock would appear to be ticking much more slowly, and you would seem to be moving in slow motion. This isn't because the observer on Earth is seeing things wrong, it's because time itself is actually passing more slowly for you, the person travelling at high speed. This effect, while strange, has been confirmed by many experiments. One of the most famous of these experiments involves the use of atomic clocks, which are incredibly precise timekeeping devices. In the 1970s, scientists conducted an experiment where two atomic clocks were synchronized, and then one was flown aboard a fast-moving airplane while the other remained on the ground. When the clocks were compared after the flight, the clock aboard the plane had experienced less time, confirming that time had passed more slowly for the fast-moving clock. This experiment is just one example of how time dilation is not just a theoretical concept. It's a real, measurable phenomenon. The implications of time dilation are vast and far-reaching. If time behaves this way for objects moving at high speeds, it means that astronauts travelling in space at velocities near the speed of light could age more slowly than people on Earth. A journey that might take only a few years for the astronauts could span centuries on Earth. This concept has been popularised in science fiction, but it's based on solid physics. The idea of time dilation is not just a theoretical curiosity, it has real-world applications, such as in the functioning of GPS satellites. GPS satellites, which orbit Earth at speeds of about 14,000 kilometers per hour, are a practical example of how relativistic effects must be accounted for in modern technology. The clocks on these satellites tick slightly faster than those on Earth due to their high velocity and the weaker gravitational field they experience in orbit. According to general relativity, clocks run slower in stronger gravitational fields, so on Earth, where gravity is stronger, time moves more slowly. In order for the GPS system to provide accurate location data, these relativistic effects must be taken into account. If they weren't, the system would drift by several kilometers each day, making it unreliable. This brings us to length contraction, the second of the major relativistic effects. Length contraction refers to the fact that objects appear shorter in the direction of motion as they approach the speed of light. This effect occurs along with time dilation and is a consequence of the way space and time are intertwined in the fabric of space-time. To a stationary observer, a spaceship travelling at high speed would appear to be compressed or contracted along its length. If you were aboard the spaceship, you wouldn't notice this contraction, but someone on Earth would see the ship as shorter than it would be if it were at rest. It's important to note that this length contraction only happens in the direction of motion. If the spaceship were travelling in a straight line, the contraction would occur along its length, but its height and width would remain unaffected. The closer the spaceship's speed is to the speed of light, the more pronounced the contraction would be. At speeds that are not close to the speed of light, the contraction would be imperceptibly small, but as the speed increases, the effect becomes more significant. For objects moving at light speed, if that were possible, the length would shrink to zero, and it would take an infinite amount of energy to reach that speed. This is one of the reasons why no object with mass can travel at the speed of light. Both time dilation and length contraction have been confirmed experimentally, and they are central to the way we understand the universe at both the large and small scales. But how do these ideas fit into the broader structure of special and general relativity? In special relativity, which deals with objects moving at constant speeds in straight lines, the relationship between space and time is defined by the Lorentz transformations. These mathematical equations describe how time and space are perceived differently by observers moving at different speeds. The speed of light is the key to these transformations, and it serves as the ultimate limit for how fast information can travel through space. In general relativity, Einstein extended his theory to include gravity and acceleration, showing that the curvature of space-time itself could influence the flow of time and the length of objects. In the presence of a strong gravitational field, such as near a massive planet or a black hole, time moves more slowly, and objects may appear contracted. General relativity takes the principles of special relativity and applies them to the more complex situation, where objects are accelerating or experiencing gravitational forces. The connection between these two ideas, time dilation and length contraction, lies in the concept of space-time. In the relativistic view, space and time are not separate, independent entities. They are part of a unified four-dimensional framework. Time dilation and length contraction are two manifestations of how the geometry of spacetime changes depending on the speed of an object and the gravitational field it's in. These effects are crucial for understanding the true nature of the universe, where space and time are interconnected and can be altered by motion and gravity. As we dive deeper into the effects of light speed, it's clear that they go beyond mere theoretical curiosity. These relativistic effects, which seem so strange to our everyday experience, are actually essential for our understanding of the universe. They are not just abstract ideas, they shape the way we experience time, the way we measure distances, and even the way we navigate the modern world. From the time-dilating effects of high-speed space travel to the adjustments made in GPS systems, relativity is a crucial part of our technological landscape. As we continue to explore the deeper implications of light speed, we'll start to see how these relativistic effects challenge not only our understanding of space and time, but also the very nature of reality itself. And as we transition from these physical effects to the philosophical questions they raise, we begin to realize that the speed of light is not just a scientific constant, it's a gateway to understanding the fundamental principles that govern everything from the smallest particles to the vastest stretches of the cosmos. The constancy of light speed has more than just scientific implications. It has profound philosophical ramifications that challenge how we perceive the very nature of reality itself. For centuries, we have lived with the assumption that time and space are fixed, unchanging entities, always moving in the same direction. But as we've seen, the speed of light is a cornerstone of modern physics that challenges these assumptions, forcing us to rethink not just the workings of the universe, but how we experience it. One of the philosophers who grappled with the nature of time and space in ways that are deeply relevant to our understanding of light speed was Henri Bergson, a French philosopher in the late 19th and early 20th centuries. Bergson famously argued that our perception of time, which he referred to as la durée, duration, is vastly different from the way time is measured by clocks or scientific instruments. According to Bergson, time in our everyday experience is fluid and subjective, a process that can't be captured by rigid measurements or the ticking of a clock. This stands in stark contrast to the way that time is portrayed in the equations of physics, where it is treated as a constant, immutable dimension. Bergson's ideas challenge us to consider the human experience of time, and by extension, how we relate to the speed of light. Light speed is a universal constant, but how do we experience it? Does it influence how we understand the flow of time in our everyday lives? In the relativistic view of physics, time is not a universal experience. Time moves differently for observers in different frames of reference. If you're travelling at a speed close to that of light, for example, your perception of time changes drastically compared to someone who remains at rest. Time slows down for you, but the person at rest experiences time at its normal pace. The constancy of light speed, then, has a deep connection to how time is understood in relativity, and this challenges our basic intuitions about the flow of time in the world we experience. The implications of light speed extend beyond our personal experience of time and stretch into our understanding of the universe itself. In the relativistic view, space and time are linked in a four-dimensional framework called space-time. The speed of light plays a crucial role in this structure. Light speed is the speed at which information can travel, and it sets the ultimate limit on how fast we can communicate or influence events across the universe. This limit has far-reaching consequences for the nature of causality, the idea that cause precedes effect. In classical mechanics, the separation between cause and effect is clear-cut. If you push an object, it moves in the direction of your push. The cause, your force, comes before the effect, the object's motion. But in the relativistic framework, the relationship between cause and effect becomes more subtle. If information or an influence can't travel faster than the speed of light, this creates a boundary between events. Events that are separated by a distance greater than the speed of light's travel time are causally disconnected. They cannot influence each other because any signal trying to travel between them would take too long to cross. This means that the constancy of light speed is deeply woven into the very fabric of causality itself. It shapes the limits of what is possible, both in the universe at large and in our understanding of cause and effect. In addition to shaping our understanding of time and causality, light speed is also linked to the nature of reality. In a sense, light acts as the bridge between the known and the unknown, allowing us to observe and measure the universe. When we look at the stars, for example, we are not seeing them as they are right now, but as they were when their light left them. The light from the sun takes approximately 8 minutes to reach us, meaning that we are always looking into the past when we observe our nearest star. The farther away an object is, the further back in time we are seeing it, as the light takes longer to reach us. This introduces an interesting perspective on the universe's observable properties. The farther we look into space, the further we look into the past, and the more we are constrained by the speed of the light. Our knowledge of the universe is limited by how far light has been able to travel since the Big Bang. This means that we are constantly restricted in our observations by the speed of light. If light's speed were different in the past, especially in the early universe, it could have significant consequences for how we understand cosmic evolution. For instance, if the speed of light were faster during the early universe, we might have been able to observe events that occurred during a period of cosmic inflation in much greater detail. This raises a fundamental question about the relationship between the speed of light and the nature of the observable universe. If light can travel faster, could we have more access to the past than we do now? Could we observe distant galaxies with a clarity we cannot even begin to fathom? These questions lead us to reflect on how light speed, as a universal constant, influences not only the physical laws of the universe, but also the very way in which we, as conscious beings, understand the cosmos. Our perception of the universe is shaped by the limitations of light speed. The very fact that light travels at a finite speed means that we can never see the universe as it is right now. We are always looking into the past. This limitation forces us to reconsider the nature of reality itself. What does it mean to observe the universe if our observations are always delayed? What if, like Bergson suggested, time itself is not a linear flow, but something more flexible, something more subjective, and we are just experiencing a fraction of that deeper hidden reality? The constancy of light speed touches on deeper philosophical ideas about the nature of existence. If light speed is fixed, then what does that tell us about the underlying structure of space and time? Is there something inherent about the universe that forces light to move at this particular speed? Or is this just an arbitrary feature of the universe, a constant that simply exists because it does? These questions don't just challenge our scientific models, they also raise profound questions about the nature of knowledge, perception, and reality. Looking forward, it's clear that the study of light speed will continue to shape the future of physics. Whether or not light speed varies over time, whether new theories of quantum gravity reveal new insights, or whether our understanding of space-time itself evolves, light remains the key to unlocking the deepest secrets of the universe. As we push the boundaries of our knowledge and venture further into the unknown, the philosophical implications of light speed will continue to guide our understanding of not just the universe's mechanics, but the very nature of existence itself. Understanding the speed of light is not just a scientific endeavour, it is a journey into the heart of reality, one that will continue to unfold in surprising and exciting ways. As we move further into the quantum realm, the behaviour of light becomes even more intriguing and complex, challenging everything we thought we knew about its nature. In the classical world of physics, light was long understood to travel as an electromagnetic wave, governed by the laws of Maxwell's equations. However, as quantum mechanics began to take shape, it quickly became clear that light's behavior was far more mysterious than simple wave dynamics could explain. This realization led to the birth of quantum mechanics, a framework that not only revolutionized our understanding of light, but also brought forward entirely new theories about how it behaves, especially in the context of the tiniest scales of reality. Quantum mechanics teaches us that light can behave both as a wave and as a particle. This is known as wave-particle duality. Light's particle form, called a photon, is responsible for many of the quantum phenomena we observe, such as the photoelectric effect, which was famously explained by Albert Einstein in the early 20th century. While the wave description of light still holds true at larger scales, at the quantum level, light doesn't neatly fit into any one category. This strange behavior forces us to rethink not only light's interactions with matter, but also the very structure of reality itself. One physicist whose work has had a lasting impact on our understanding of quantum mechanics and the behavior of light is Hugh Everett. In the 1950s, Everett introduced the many worlds interpretation of quantum mechanics, which radically altered how we think about the role of observation in the quantum realm. According to Everett, every time a quantum measurement is made, the universe splits into multiple parallel realities, with each possibility realized in a different world. In this framework, light's behavior could be understood in terms of different quantum realities, where the speed of light might be influenced by the specific world in which it exists. This perspective opens up intriguing possibilities for understanding how light behaves in different quantum realities. If light can be part of many different versions of reality, then the speed of light might not be a universal constant across all of them. In some worlds, the speed of light might be slightly different, or its behavior might take on forms that we can't currently observe in our own reality. Everett's work challenges the classical view that there is one objective reality that governs all physical processes. Instead, he proposed a model where reality is a complex branching tree, with light behaving differently in each branch. This radical shift in thinking highlights just how far our understanding of light has evolved since the days of classical physics. Alongside the ideas of Everett, another fascinating concept that has emerged in recent years is quantum entanglement. This phenomenon, first predicted by Einstein, Podolsky and Rosen in the 1930s, and later experimentally confirmed, suggests that two particles can become entangled, meaning that the state of one particle is instantaneously linked to the state of another, no matter how far apart they are. This connection appears to defy the limits set by the speed of light, as information about one particle's state seems to travel instantaneously to the other, even across vast distances. The phenomenon of quantum entanglement raises profound questions about the nature of light and its speed. If two photons become entangled, does the speed at which the information is transmitted between them have anything to do with the speed of light? In the traditional view of physics, nothing can travel faster than the speed of light, and yet quantum entanglement suggests that some form of instantaneous communication between entangled particles occurs, even across distances that would take light years to traverse. This doesn't violate the speed of light limit, because the process doesn't transmit any usable information faster than light. Still, it challenges our understanding of how light and other particles interact across space. Entanglement also raises questions about the fundamental nature of space itself. If two particles can be linked instantaneously, regardless of distance, then what does this say about the geometry of space-time? Does this imply that space, in its most basic form, might not be as separate and disconnected as we once thought? Could the structure of space-time allow for connections beyond what we perceive as the speed of light? These are the kinds of mysteries that quantum mechanics presents to us when we think about the speed of light and its role in the universe. As we continue to explore the implications of quantum mechanics, one of the most exciting developments in our understanding of light comes from quantum field theory, or QFT. Quantum field theory is the framework that combines the principles of quantum mechanics with special relativity. It treats light not just as a particle or a wave, but as a fundamental excitation in the electromagnetic field. In this view, light is a manifestation of the quantum field itself, and its speed is an emergent property of that field. The behavior of the electromagnetic field, and by extension the speed of light, is influenced by the underlying quantum dynamics that govern particles and forces. In the context of QFT, light's speed is not merely a fixed constant, It is a result of how the electromagnetic field interacts with other quantum fields. The speed of light, as we observe it, might be a consequence of the properties of the quantum vacuum, a state that is not truly empty, but is filled with fluctuating fields. These fields can influence the speed at which light propagates, and they are deeply connected to other fundamental forces in the universe, such as gravity and the strong and weak nuclear forces. This link between light speed and the quantum fields opens up new possibilities for understanding phenomena like dark matter and dark energy. These mysterious substances, which make up most of the universe's mass and energy, have largely remained unexplained. However, some physicists have speculated that the behavior of light might be connected to these unknown forces. For example, if light speed were influenced by the presence of dark matter, then the interactions between light and these elusive particles might hold the key to understanding their nature. Similarly, dark energy, which is thought to be responsible for the accelerated expansion of the universe, could potentially interact with light speed in ways that we don't yet fully understand. Another exciting possibility comes from string theory, a theoretical framework that attempts to unify all of the fundamental forces of nature into a single, coherent theory. According to string theory, the fundamental particles of the universe are not point-like objects, but rather tiny vibrating strings. These strings can exist in higher dimensional spaces, and their vibrations determine the properties of particles and forces. In this framework, the speed of light might not be constant in the way we currently understand it. Instead, it could be influenced by the specific configuration of strings and the extra dimensions that exist beyond the three spatial dimensions we observe. String theory suggests that light might behave differently at extremely small scales, where the effects of quantum mechanics and gravity are most pronounced. In these extreme conditions, such as near a black hole or in the very early universe, the speed of light might vary, or it might interact with other fundamental forces in ways we can't yet observe. While string theory is still speculative and has not been experimentally verified, it presents a tantalizing possibility that the speed of light is not a simple constant, but rather something that could change under certain conditions. As we continue to push the boundaries of our understanding of light's behavior, we are bound to encounter new insights that challenge the very nature of reality. Whether it's through quantum entanglement, quantum field theory, or the speculative ideas of string theory, light remains at the center of some of the most profound questions in modern physics. The mysteries of light's speed and its role in the quantum world offer a glimpse into a deeper reality, one where our classical notions of space, time, and causality no longer apply. Looking forward, the future of physics holds exciting possibilities as we explore light's behavior at the quantum scale. New technologies, experiments, and theories will continue to expand our understanding of light, revealing new dimensions of the universe and perhaps even new laws of nature. As we venture further into the quantum realm, light will remain one of our most important clues in unlocking the deepest secrets of the cosmos. Understanding the speed of light isn't just an academic pursuit. Its implications have far-reaching practical applications that shape the technologies we rely on every day. From communications to navigation to the very foundation of modern physics, the constancy of light speed is at the heart of many of the technologies that drive our world forward. The way light behaves and the fact that it travels at a constant speed in a vacuum has allowed us to build complex systems that harness this fundamental property to perform tasks that were once thought impossible. One of the most prominent examples of light speed being put to use in modern technology is fiber optics. Fiber optic technology relies on light's ability to travel through glass or plastic fibers at incredibly high speeds. These fibers are designed to transmit data in the form of light pulses, and they are capable of carrying vast amounts of information across long distances with minimal signal loss. Fiber optic communication is the backbone of the modern internet, and it allows for incredibly fast data transfer rates, making video streaming, video calls, and global communication possible. The entire system depends on the fact that light can travel through these fibers almost without delay, with speeds that are close to its theoretical maximum. In fiber optics, engineers have to take into account not only the speed of light, but also how it behaves in different materials. Light slows down slightly when it passes through glass or other mediums, but it still travels at speeds that are much faster than traditional electrical signals. This speed is what enables the transfer of data over great distances without significant loss of information, allowing us to stay connected across the globe. The constancy of light speed means that we can predict how long it will take for data to travel from one place to another, ensuring that communication networks can be designed with precision. Another area where the speed of light plays a crucial role is in the functioning of GPS systems. Global Positioning System satellites orbit Earth and provide precise location data to devices on the ground. The GPS system relies on a network of satellites that continuously broadcast signals, and these signals travel at the speed of light. The satellite's clocks are synchronized with atomic precision, and by measuring the time it takes for the signal to travel from the satellite to a GPS receiver, the system can calculate the distance to each satellite. By triangulating this information from multiple satellites, the receiver can pinpoint the user's location anywhere on Earth. However, the speed of light isn't just a factor in how signals travel, it also requires adjustments for relativistic effects. GPS satellites orbit at high speeds and are farther from the Earth's gravitational field than receivers on the ground. This means they experience time slightly differently due to the effects of both special and general relativity. As predicted by Einstein's theories, the clocks on the satellites tick slightly faster than those on the ground. Engineers must account for these time differences, correcting for the relativistic effects so that the system can provide accurate location data. Without these adjustments, GPS systems would quickly drift out of sync, rendering them useless. In addition to communication and navigation, the constancy of light speed also underpins technologies such as particle accelerators, where scientists attempt to speed up particles to velocities close to that of light. In particle accelerators, like the Large Hadron Collider, light speed serves as the ultimate limit. Scientists accelerate particles to nearly the speed of light, and then collide them to study the fundamental particles that make up the universe. The behavior of light, and the understanding that it cannot exceed a certain speed, provides the boundaries within which these experiments can be designed. The speed of light constrains how high-energy experiments can be conducted, influencing the designs of future particle colliders and even our understanding of what can and can't happen at extremely high energies. Looking further into the future, the speed of light continues to inspire the development of emerging technologies. Quantum computing, for example, relies on the behavior of quantum bits, or qubits, which are capable of existing in multiple states simultaneously. Quantum computing promises to revolutionize industries by solving problems too complex for even the most powerful traditional computers. Light plays a key role in quantum computing, especially in the form of photonic qubits, which use photons to carry quantum information. The speed at which light moves, and the ability to manipulate and control light at the quantum level, will be crucial for advancing this technology. As scientists continue to explore the quantum properties of light, we may unlock entirely new ways to compute, communicate, and interact with information. However, light speed presents challenges even in the realm of quantum computing. Quantum entanglement and teleportation, phenomena where information can be transferred instantaneously, seem to contradict our understanding of the speed of light. But while these processes appear to defy the limitations set by light speed, they don't actually violate any physical laws, as no usable information is transmitted faster than light. Nonetheless, the exploration of these phenomena in quantum technologies continues to challenge our assumptions about the limits of speed, suggesting that the way light behaves at the quantum level might not follow the same rules we observe at macroscopic scales. As for space exploration, the light barrier also plays a critical role. The vast distances between stars and galaxies mean that space travel is limited by the speed at which information can travel. Even if spacecraft could travel close to the speed of light, it would still take years, decades, or even centuries to reach distant stars. Current space exploration technologies are constrained by the fact that light, the fastest thing we know, takes years to travel between stars. For example, the closest star system to Earth, Alpha Centauri, is about 4 light-years away. If we were able to send a spacecraft traveling at 1/10 of the speed of light, it would still take 40 years to reach Alpha Centauri. The challenge of overcoming the light speed barrier remains one of the most significant hurdles in the quest for interstellar exploration. However, scientists and engineers are exploring new ideas to overcome these challenges. Concepts like the Alcubierre drive, which is a speculative idea based on general relativity, suggest that it might be possible to create a warp bubble that could contract space in front of a spacecraft and expand it behind, effectively allowing the spacecraft to travel faster than the speed of light, without violating any fundamental laws of physics. While this idea is purely theoretical and faces enormous technical challenges, It highlights the ongoing drive to push the boundaries of space exploration. As we continue to push the frontiers of technology, the constancy of light speed remains both a foundation and a limit. It defines the pace at which information, energy, and matter can move, shaping everything from communication systems to space travel. As we explore the quantum world and continue to refine our understanding of light's behavior, we may uncover new insights that redefine what we thought was possible. Light speed may very well remain the ultimate boundary, but as we look toward the future, it could also become the key to unlocking new technologies that revolutionize how we interact with the universe. As we stand at the cutting edge of scientific discovery, the future of light and our understanding of its behavior promises to be as awe-inspiring as it is transformative. For centuries, we have treated the speed of light as a constant, woven into the very fabric of the universe. Yet the more we learn about the nature of reality, the more we realize that light and its speed might still hold secrets that could reshape our entire understanding of the cosmos. One of the most tantalizing possibilities for the future of light lies in the potential discovery of variations in its speed. Could light speed change depending on the conditions of the universe, perhaps in different regions of space or at different points in time? Scientists have long speculated that in the early universe, shortly after the Big Bang, the speed of light might have been vastly different. Some theories, like those of João Magalhães and the varying speed of light (VL hypothesis), suggest that the speed of light could have been much faster in the first moments of the universe's existence, potentially allowing for the rapid expansion known as cosmic inflation. If such variations in light speed were to be confirmed, it could provide new insights into the fundamental principles that govern the universe, forcing us to rethink everything from the structure of space-time to the nature of the forces that shape it. But even beyond the possibility of varying light speeds, there are a host of new ideas that could radically alter our understanding of light's place in the cosmos. One such idea comes from the field of quantum gravity, which seeks to combine the seemingly incompatible theories of quantum mechanics and general relativity. Quantum gravity aims to describe the behavior of gravity at the quantum level, where the effects of both quantum mechanics and relativistic gravity are important. In the search for a unified theory of quantum gravity, scientists have speculated that the speed of light might not be constant across all scales, particularly in extreme environments such as black holes or the very early universe. One approach to quantum gravity is string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. In this framework, the properties of light, including its speed, could be influenced by the configuration of these strings and the extra dimensions that string theory predicts. String theory suggests that the universe is made up of more than just the three spatial dimensions we experience. There could be many more hidden from our direct observation. If light speed were to vary depending on the configuration of these extra dimensions, it would radically change how we think about the fundamental constants of nature, including the speed of light itself. Another speculative idea that has emerged in recent years is the holographic principle, which suggests that the universe may be a kind of projection from a lower dimensional surface. According to this theory, all of the information in our three-dimensional universe could be encoded on a two-dimensional boundary, much like a hologram. In this framework, the speed of light could be tied to the way information is encoded and processed on this boundary, and its behavior could be linked to the fundamental laws that govern the universe at the highest level. While the holographic principle is still an area of active research, its potential to reshape our understanding of light speed is profound, as it suggests that light might be just one manifestation of a deeper, underlying reality. As these theories continue to evolve, experiments designed to test the fundamental properties of light are ongoing. Some of the most promising research comes from the study of the cosmic microwave background, CMB radiation, which provides a snapshot of the universe when it was just a few 100,000 years old. The CMB holds clues about the early universe, including whether light speed might have been different in the past. By analyzing the fluctuations in the CMB, scientists hope to detect subtle signs of variations in the speed of light, which could provide direct evidence for VSL theories and offer new insights into the origins of the universe itself. In addition to studying the cosmic microwave background, other experiments are being conducted to investigate how light behaves in extreme environments, such as near black holes or in the presence of strong gravitational fields. Light's behavior in these regions, where space-time is intensely curved, could offer clues about the true nature of light speed. For example, the bending of light around black holes, known as gravitational lensing, provides a way to probe the structure of spacetime and test the predictions of both general relativity and quantum gravity. If light speed is influenced by gravitational fields in ways that we don't currently understand, these observations could offer a new avenue for research. Another exciting possibility for future experiments involves the study of high-energy particles in accelerators. Particle accelerators, such as the Large Hadron Collider, allow us to probe the universe at extremely small scales, where quantum effects dominate. As scientists continue to push the limits of particle accelerators, they may uncover new ways in which light speed is linked to the fundamental properties of matter and energy. For example, experiments involving high-energy photons or particle collisions might reveal subtle variations in light speed under extreme conditions, opening up new insights into the behavior of light at the quantum level. In the realm of technology, the future of light holds tremendous potential. Quantum computing, for instance, relies on the manipulation of light at the quantum level. Quantum bits, or qubits, can exist in multiple states simultaneously, allowing quantum computers to perform certain types of calculations exponentially faster than classical computers. As researchers develop more sophisticated quantum computing technologies, the speed at which light can be manipulated and controlled will be crucial for advancing the field. Photonic qubits, which use photons to represent quantum information, could one day lead to computers that harness the fundamental properties of light to perform calculations that are currently beyond our reach. Likewise, the potential for faster-than-light communication, though still speculative, continues to capture the imagination of scientists and engineers alike. Concepts like quantum entanglement and teleportation, where information seems to be transmitted instantaneously across vast distances, hint at the possibility of communication that transcends the speed of light. While these phenomena do not allow for faster-than-light travel in the traditional sense, they could still lead to breakthroughs in how we transmit information and interact with the universe on a fundamental level. If future theories and experiments can unlock the secrets of these phenomena, they might pave the way for technologies that seem straight out of science fiction. As we move into the future, the ongoing quest to understand light's behavior will continue to shape both our scientific and technological advancements. Whether through the development of new quantum theories, the discovery of variations in light speed, or the pursuit of faster-than-light communication, the next few decades hold exciting potential for unraveling the deepest mysteries of the universe. The speed of light, once considered a fixed and immutable constant, may be far more dynamic than we can imagine, and it is through exploring these possibilities that we'll continue to expand the boundaries of human knowledge. Looking ahead, the discoveries we make about light speed will not only reshape our understanding of the cosmos, but will also have a profound impact on the technologies we rely on every day. As we continue to explore the fundamental nature of light, we may find that the answers to these questions hold the key to unlocking some of the most significant breakthroughs in both science and technology, driving us to new frontiers of discovery and innovation. The journey to understand the speed of light has been one of the most profound and transformative quests in the history of human thought. From the early experiments of Galileo and Fizeau, who first measured light speed, to the revolutionary insights of Einstein, who showed us that light speed is central to the very fabric of space and time, our understanding of light has evolved in ways that continue to shape the course of science. And yet, as we've explored throughout this journey, light speed is not just a scientific curiosity. It is a key that unlocks some of the deepest mysteries of the universe. As we have seen, light speed lies at the heart of some of the most fundamental concepts in physics, from relativity to quantum mechanics, from the structure of space-time to the nature of time itself. The constancy of light speed has shaped our understanding of everything from the expansion of the universe to the development of cutting-edge technologies like GPS and fiber optics. But beyond these practical implications, the speed of light raises philosophical questions that challenge our perception of reality. How do we reconcile the flow of time in our everyday experience with the strange and counterintuitive effects of relativity? What does it mean for our place in the universe if the speed of light is the ultimate limit of communication and causality? As we dive deeper into these questions, we encounter not just scientific theories, but also ideas that stretch the boundaries of human imagination. The speculative nature of concepts like varying speed of light theories and quantum gravity pushes us to rethink the very structure of space and time. Could light have travelled faster in the early universe, altering the course of cosmic history? Is it possible that light's behaviour might be influenced by quantum fields or extra dimensions, as string theory suggests? These theories invite us to think beyond our current understanding and challenge us to imagine a universe where the rules of physics are not as fixed as we once believed. At the same time, the ongoing quest to understand light's speed is not just about pushing the boundaries of theoretical physics. It's about bridging the gap between our scientific knowledge and our philosophical understanding of reality. The constancy of light's speed, while seemingly simple, holds profound implications for how we perceive time, space, and causality. As scientists continue to explore the quantum realm, the relationship between light and gravity, and the fundamental nature of space-time itself, new insights will continue to emerge, insights that will undoubtedly reshape our view of the universe. The philosophical and scientific implications of light speed are not just academic exercises. They have real-world consequences, influencing the technologies that shape our lives, from the telecommunications that connect us across vast distances to the satellites that navigate our world. Light speed is woven into the fabric of modern life. As we continue to refine our understanding of how light works, we open up new possibilities for technological advancements that can transform the way we live, communicate, and explore the universe. As we reflect on these ideas, it's clear that the study of light speed is far from complete. While we've made tremendous strides in understanding the fundamental principles that govern the speed of light, there is still so much to discover. New theories and experiments will continue to expand our knowledge, offering new perspectives on the nature of light, time, and space. Perhaps in the future we will discover new ways to manipulate light's speed, or uncover hidden dimensions of reality that change the very way we perceive the universe. For the next generation of scientists and thinkers, the speed of light will remain a cornerstone of inquiry. It will continue to be a guiding force in the search for new theories of quantum gravity, dark matter, and the fundamental forces of nature. And, just as it has shaped the course of science in the past, the ongoing exploration of light's speed will shape the future of physics, technology, and our understanding of the cosmos. As we look toward the future, we are reminded that the quest to understand light's speed is not just a journey into the unknown. It is a journey that connects us all, across space, time, and reality itself. Light's speed, in all its mystery and wonder, offers a glimpse into the deepest truths of the universe, and it is through this pursuit of knowledge that we continue to evolve our understanding of the world around us. The mysteries of light, space, and time are waiting to be uncovered, and as long as we continue to ask questions and seek answers, we will never stop discovering the vast and wondrous universe we inhabit. Throughout our exploration of light speed, we've ventured through both the scientific and philosophical realms, uncovering layers of understanding that challenge our view of the universe. From the early measurements of light speed by scientists like Galileo and Fizeau to Einstein's revolutionary theories of relativity, light has always been central to our quest to comprehend space, time, and reality itself. We've seen how light's constancy shapes our modern technologies, from the fibre optics that power our internet connections to the GPS satellites that help us navigate the world. We've also touched on the more speculative and theoretical aspects of light, exploring the possibility that light's speed might have been different in the early universe, or that it might even vary in extreme conditions, as suggested by ideas like the varying speed of light theory. These possibilities raise profound questions about the very fabric of space and time, opening new doors to understanding the deepest laws of nature. The relationship between light speed and the fundamental forces of the universe has also led us to rethink concepts like causality and the flow of time. The insights of thinkers like Henri Bergson, who questioned our perception of time, and the ongoing work of physicists developing quantum gravity and string theory, remind us that light is not just a measurable quantity, but a window into the nature of reality itself. It's both a scientific constant and a philosophical puzzle, shaping our technology, our understanding of the cosmos, and our place within it. As we continue to advance our understanding of light's role in the universe, the scientific community is poised to make even more groundbreaking discoveries. Whether through experiments probing the cosmic microwave background, exploring quantum entanglement, or developing next-generation quantum computers, the mysteries surrounding light's speed promise to deepen as our tools and theories evolve. As we conclude this journey, it's important to remember that the quest for knowledge is never static. With each new discovery, we're not just learning more about light's speed, we're unraveling the very nature of the universe itself. The future is filled with endless possibilities, and the frontier of light's behavior continues to expand. So, stay curious. The universe is vast, and there are still many mysteries waiting to be uncovered. Whether you're a scientist, a thinker, or just someone wondering about the world around you, remember that the search for knowledge is an ongoing adventure. There are more questions to ask, more discoveries to make, and who knows, perhaps the greatest revelations are still ahead of us. As we continue to explore the speed of light, we also continue to explore the limits of our understanding, one question at a time.